Chapter 5, suitable for a practice test for the exam. It's always important to think about how you would use a video discussing a practice test. If you've worked on the problems authentically, they're going to give you feedback in a different way than if you haven't really given them a try without notes. So take a second, reflect. Have you used the practice exam authentically, or are you just coming to look at the shown work? Here's the different sections within Chapter 5. It's important leading into an exam to do what the folks describe as transforming instructional materials. Instead of taking the notes and the previous resources and just sort of looking at them, it's important to take them and internalize them and generate your own understanding. It would be great if you could take each section of Chapter 5 and summarize it in a very targeted way that would help you answer questions correctly on the exam. Can you take each of the different sections and write yourself some notes? Can you make a cheat sheet that would allow you to get questions right in that section? Is that a skill you have? Do you have some that you can do that for and others that you can't? Share your thoughts. As we go through these, I'm going to share with you my thoughts for how I would summarize the information for my own summary page. So within here, I see two questions pertaining to potential energy. So what's coming into my mind, what I would be using would be like this figure that we have at the top, where we see that it goes to a smaller, more negative potential energy when we have opposite charges coming closer together. And if we have like charges coming closer together, the potential energy is going up. It's increasing, becoming more positive. And our potential energy of 0, our reference is set where the particles are far apart from each other. So as I read each of these, how does the potential energy change when you have a positive and a negatively charged sphere and they're moved closer together? I think the potential energy is becoming more and more negative. It's getting to be a smaller and smaller value. The second question, same kind of thing. It's showing us a representation of the charged spheres at different distances. I see the signs can be different and also the magnitude of the charge can be different. I have two examples with positive, positive or negative, negative. Both of those would be leading to a positive potential energy. They're shown to be quite close together, but the one with the greater charges leads to a more positive potential energy. -1 and -1, that would also be a positive potential energy, but because they're smaller charges, it's not as positive. You could think about it as stronger magnets versus weaker magnets. At the same distance, you'd have a greater force of attraction when the magnets are stronger. This would be the one that would be closest to 0 because the particles are farthest apart from each other. They're approaching our reference value of P. The potential energy equals 0 at a large separation. Within this one, I see some questions involving heat and work. This is what's coming to mind for that. When I'm thinking of heat, something that's exothermic, the Q value would be negative. The change in enthalpy would also be negative, and heat's leaving the system. When it's endothermic, heat's entering the system, positive value for the heat or for the enthalpy change. Heat's entering the system. When it comes to the work, if the volume of the system is increasing, the work is negative. The work is being done by the system. And if the volume of the system is getting smaller, the work is positive and work is being done on the system. Heat and work are two ways that you can change the internal energy. So for this first one, it's exothermic, and it does 200 kilojoules of work. So in both of those cases, the sign is negative. So the change in internal energy would be -700 kilojoules. Take a second. Given this information, how would you interpret this next scenario? I think the water freezing is the system that was exothermic. It left the bottle as the water became ice. The volume increased enough so it cracked the bottle. Work was being done by the system. So this would be a case where the sign would be negative for both those examples, for both heat and work. Here we have information with a balanced chemical equation and the corresponding delta H, and we're connecting it to the stoichiometry. So for this one, this is how I sort of summarize it for myself. I want to remember that when I have a delta H value, that's corresponding to the energy that's involved when the coefficients are mole amounts. With that information, I can connect it to these other stoichiometry problems. So within this case, within our balanced equation, we had 3.5 moles of methane, 4 moles of the O2. In the balanced equation, we have coefficients of 1 and 2. So if I just track it through with a BCA table, I see that my limiting reactant in this scenario was the O2. Looks like we could have all 4 moles of it consumed. In the balanced equation, it's for 2 moles. We have enough oxygen present within this scenario to double all the coefficients. 2 moles of O2 produced 890 kilojoules. So if I have 4 moles involved, how much would it be? It would be just double. So if I wanted to report it as a delta H, I could give a negative sign. The amount of heat that was produced was 1,781 kilojoules of heat. Second one there, the scenario says it produces 575 kilojoules. If all of the coefficients are mole amounts, it would have produced 890. So less heat was produced. We didn't reach 890. We don't have 1 mole of methane and 2 moles of O2. Less of that reacted. How much less? Well, if I set it up as a simple ratio, it's about 65%. So 1 mole of methane, given that ratio, would be 0.646 moles of methane. That's what it would be proportionally if I was going to produce the 575 kilojoules. How many grams of the methane that would be involved? Well, 1 mole is 16 grams. We don't have 16 grams that got consumed. We have about 65% of it. That was a 10.3. Same reasoning here for the O2. Based on the balanced coefficients, 2 moles of O2 would have been involved in a reaction that gave me 890 kilojoules. But I don't have a reaction that gave me 890, it gave me 575. So I only have about 65% of the O2 compared to that coefficient of 2. So I used up about 1.292 moles of O2, and I could convert that into grams. All I'm doing is having a rescaling. If these were values of 1 mole and 2 moles, it would have given me 890. In a sense, I'm finding out what would be the smaller coefficients if it's producing 575. This is a Hess's Law problem. My reminder for this one for myself, I first want to look for unique products or reactants to match up. When I reverse an equation, I'm going to change the sign. If I change the coefficients, I change the amount for the delta H, and I may need to cancel along the way. So for this first one, finding a unique feature, in my target reaction here, I see that I need mercury liquid. If I look at the provided ones, it's showing up a couple times. That's not a great choice for being a unique one. CO2 would be a better choice. For CO2, I see it listed in my target equation, and I only have it listed once in the provided ones. So I know that if I get the CO2 in the correct spot using this equation, that manipulation has to be correct. Put it in the right spot, I'd have to reverse the equation because I want to have 1 mole of CO2 on the product side. So I'm going to reverse the entire equation, and when I do, I will change the sign for the delta H. Here's another unique feature. Hg2CO2, I want to have as a reactant. I only see that listed once here as a product. But if I reverse that reaction, I'll reverse the entire thing. It will put it over there as 1 mole on the reactant side, which is exactly what I want. If I reverse it, I change the sign. If we now add the whole thing together, we can see all of the terms. We'll have things cancel, and we end up with our target expression. We also add together the enthalpy values, and this would be then the overall delta H. This one here is a far more complicated example. It's still following the same rules, but this may need to cancel is a feature of it. So as I look at this one, if I'm looking for a unique feature, I see nitric acid listed as a product, and I have that listed only once in a provided reaction. So I'm going to use that one to get my nitric acid in the correct spot. I'm sure for that second reaction there, I don't need to reverse it, but I have to cut all the coefficients down by half, and the delta H gets cut down in half then. Next, how about the N2? With the one that I've just listed that I'm going to be using, I see that I have N2 listed as a reactant. But I don't have any N2 in the final. So I'm going to use this reaction right here to cancel the N2. That's how I'm going to think about it. In order to cancel the N2, I'd have to reverse this entire reaction. So I'm planning ahead and thinking, the first one I was sure was right because it placed the nitric acid in the right spot. I also had this carryover N2 that was used in that. So I'm going to get rid of that. I'm going to be planning ahead by having 1 mole of N2 on the product side. In order to do that, I had to reverse that reaction. That would be my reasoning, and that's what I mean when I say you may need to cancel. How will I use that last reaction? The final reaction, which is listed right there at the top. Well, I see that in my target one, I need to have 1 mole of NO. Right now, if I look at all of the features that I've already used, I've got 2 moles of NO listed as a reactant. So the only way I can add together with this final one and get 1 mole of NO on the product side, I need to use this reaction to put 3 moles of NO on the product side. I'm saying 3 because I would have 3 on the product side, 2 on the reactant side, and it would cancel to give me 1 left over as a product. So I need to take that reaction, I need to reverse it, and I need to multiply all of the coefficients by 1.5. My reasoning for that is that will give me the correct number of NO molecules, and with my corresponding canceling, it's going to work out for me. And sure enough, it does. This is a more complex one, certainly, but it's still the same strategy, and by combining it all, I get the overall enthalpy change. This one had quite a bit of internal canceling that we had to look at along the way. This would be the most difficult kind of Hess's Law question. Within both of these, I'm seeing questions involving heat capacity. Equation that pops into my head for that is that the heat involved includes a term for the specific heat, the mass, and the change in temperature. The specific heat, it might be in joules per gram K, in which case my mass would be in grams, but we could also look for it in different units as well. This is looking for it in terms of a molar heat capacity. So it's looking for the heat capacity, not per gram, but per mole. But it's still the same kind of expression. A certain amount of heat's involved. I've got my scaling factor, which is the molar heat capacity. I converted 25 grams of copper to how many moles that was, and I have the change in temperature. If I solve for the missing molar heat capacity, 24.8 joules per mole K. Different ways you could do this. You could have went through it first of all and solved for it in terms of the specific heat in grams and then converted that to moles. That would be another way that you could do it. The second one right here, this is also one involving heat capacity. It's a little bit more involved. So in this scenario, you have a piece of metal that's 50 grams that has a specific heat of 0.380 joules per gram K. And that's initially at 85 degrees C. It's then put into 100 grams of water, which is at a lower temperature at 25 degrees C. What would be the final temperature of the container? So I know what's going to happen. They're all together in the same container. The hot metal object's going to cool down, and the water, which is at the lower temperature, is going to warm up. So it's going to meet somewhere in between those two values. It's going to be somewhere between the 85 degrees C and the 25 degrees C. So the way that I set this one up, I took the expression here for the brass. It has a specific heat, the mass of 50 grams, and then it's set up for a final condition, final temperature minus initial. I don't know what the final temperature is, but I know it was initially at 85. For the water, I have its specific heat, the mass that was involved. It's also going to be a final minus initial temperature. The final temperature is the same for both of these because the entire container is going to reach the same final temperature. So I only have one variable in the entire expression. I've set it up so that the heat from the brass and the heat from the water are set equal to 0. What this means is one of these is going to have the heat go up and the other one's going to have the heat go down. In combination, they're going to equal 0. The amount that one goes up will be equal to the amount that the other one goes down. So setting it up this way allows me personally to see that I have just one variable and allows me to solve for it more easily. So now I'm just going to follow through all of the algebra within that. I combine the specific heat times the mass for the brass, specific heat times the mass for the water. I still have final minus the initial temperature, final minus the initial temperature. I combine terms, and I find that the final temperature, 27.6 degrees. That's really close to the water. The water barely changed temperature. It was the brass that changed its temperature quite a bit. That's partly due that I had 100 grams of water and 50 grams of brass, so I had more water there. But more importantly, I had a much larger specific heat for the water. So it was much more sluggish for how much it changed. So the key thing within this, I'm setting up using that same expression, but I'm setting it for the two objects. I'm adding it together and equals 0. And once again, the reason I'm adding it together, the heat that leaves the brass is the heat that's going into the water. Same amount, just a different sign. By setting it equal to 0 for their sum, it's a way that you can have one overall expression. Here's some calorimetry questions. When I see these, I'm thinking, okay, I'm going to use the thermometer, the data for that to determine whether it's exothermic or endothermic. Second step is I would get a heat value based on the data that's provided and use specific heat or heat capacity. Third, if I have a solute dissolving, the mass that I would be using in the calculation is the mass for the total solution, the solute and the solvent put together. And then finally, these are often reported using enthalpy changes in kilojoules per mole for a particular reactant. This is my plan when I have calorimetry problems. So if I look within the first one right here, I see that the temperature goes up, so it's going to be exothermic. Get a Q value. Well, in this case, it told me what the Q value was. It involved 5,500 joules of heat. So the Q value is given. It's asking, though, to report a enthalpy change in kilojoules per mole. So I had 55 grams of a salt that has a molar mass of 68 grams per mole, so I figured out how many moles I had of that. The change in temperature, the heat that was involved was 5.50 kilojoules. So this will give me a value in kilojoules per mole, and I want to make sure it has a negative sign because based on the thermometer, it was exothermic. So this would be a setup of I'm thinking through the different steps, but I really only had to use the first step and the last step because the Q value was given. The second one is also a calorimetry one, but I put it in the conceptual category. So we have two different experiments. In the first one, we took 25 grams of a salt, we added it to 200 mils of water, and the temperature goes up. Second experiment, we use more of the salt. We use 35 grams instead of 25 grams, and we put it into 200 mils of water. And it gives me some information about the solution in each cases. But we're asked to compare each of these. What would be the same for each of these experiments? If it is the same salt dissolving, it will still have the same enthalpy change when I express it in kilojoules per mole. The whole point of expressing it in kilojoules per mole is that however much heat was involved, we're going to scale it back based on the number of moles of reactants that we have. If it is the same salt in both of these cases, it's going to have the same delta H value. It's the same process, It just had different amounts involved in the actual experiment. Those different amounts would make the Q value different. This is an exothermic process. I think it's going to have a higher temperature for experiment 2 because I have more of the salt that would be involved in the reaction. I think the final temperature would be different. I think it would be higher for the second experiment because more heat was involved. How about the sign? The sign for the delta H would be the same in both cases. Both are exothermic. In both cases, delta H is negative. This, for me, is a conceptual question that is getting at the point, how do we use the Q information to then report the enthalpy change? This is right in the standard enthalpy of formation for ammonia gas and potassium bromate. My reminder for this is I'm going to set it up for 1 mole of product, and I'm going to have the reactants. They're going to be their elements in their standard state. So if I'm making NH3, I'm going to be starting with N2 and H2. Because I'm making 1 mole of the product, fractions are okay for the reactants. For the second one, potassium in its standard state is potassium solid. Bromine is Br2 liquid. We only have 2 liquids on the periodic table under our standard conditions. Bromine is one, mercury is the other. And then O2 gas, I bet you knew that for the standard state for oxygen. And then we will put in the coefficients. Again, if we're making 1 mole of the product, fractions are okay. Here we're using standard enthalpy of formation data. I'm thinking within this one that I'm going to be using a calculation involving products minus reactants, and I want to be sure to look to the balanced equation. Here's for the first one. The products included the CO2 and the H2O. The coefficients, I had 4 of the CO2, 4 moles of that, 6 moles of the H2O. As far as minus the reactants, oxygen in its standard state won't appear in my calculation, but my ethane will. I put the whole thing in brackets for products minus reactants. The next step here, I just took the values that instead of CO2, what it actually was for the listed value. Same thing for H2O. Same thing for the ethane. I grouped everything together, and I found that this was the value for the enthalpy change for the balanced equation as written. But notice it says this is for 1 mole of ethane, not for what the balanced equation is, for 1 mole instead of 2. So I could just cut the value in half. This is another one involving standard enthalpy of formation. So I'm again thinking products minus reactants, and I want to use a balanced equation. This one's set up a little bit differently because it gives me what the overall enthalpy change is, but we're trying to find the value for one of the internal features, which was the NH3, which is a reactant. So I've set up the whole thing. I end up calling the standard enthalpy of formation for the NH3X, and I go through and I solve for what X would be. Set up the same way as the previous one though, products minus reactants, and I'm using the coefficients in the balanced equation. This is one using provided bond enthalpy data. So I grabbed a table here with some bond enthalpy data. That would be reported either in the question that you have on a test or in a table of some kind. As I'm thinking about these, I'm thinking that breaking a bond is always endothermic. Forming a bond is always exothermic. I'm going to use the provided pictures and the balanced equation. So for this first one right here, I can imagine going from the reactants to the products by breaking the bond in between the carbon and carbon. That's a double bond. Breaking the bond between the hydrogen atoms. That was a single bond. And then putting those parts back together. I'd have to form a single bond between the carbon-carbon, add a carbon-hydrogen bond, and another carbon-hydrogen bond. So I see that in this process, I would have 1 mole of carbon-carbon double bonds. I've got its value. 1 mole of hydrogen-hydrogen single bonds, got its value. Add those together, this would be the entire endothermic contribution, because breaking bonds always takes energy. Over here, I am forming carbon-hydrogen bonds. I've got 2 moles of that taking place. And I'm forming a carbon-carbon single bond. Grab those values off the table. I'm going to make that entire thing negative because this is the exothermic bond forming. I come back to my reminder here. Breaking a bond is endothermic. Forming a bond is exothermic. So anytime that I'm forming the bonds, that has to end up with a negative designation. So I'm just combining both of these, and I find it's a little bit more exothermic contribution than the endothermic, so the net change right here ends up being a negative 134 kilojoules. Here's another one where, again, I'm looking at the pictures and I'm looking at the balanced equation. In this one, the coefficients are important. In the previous one, all of the coefficients were 1. In this one, the coefficients, I have a 1, a 5, a 3, and a 4. So I have different ones that I need to account for. So I've got to be a little bit more careful with my bookkeeping. For this one, instead of breaking a select number of bonds and seeing how I'd put it back together, I'm just going to break all of the bonds to get all the independent atoms and then put them all back together. So I see that in the molecule, I have carbon-carbon bonds. I have 2 of those, 2 carbon-carbon single bonds. Carbon and hydrogen, 1, 2, 3, 4, 5, 6, 7, 8 of those, 8 moles worth. And then oxygen double bond, 5 moles of that. Those will all be endothermic because it's breaking the bonds. The exothermic contribution, oxygen and carbon, double bond, well, I see 2 of those in CO2, and I have a coefficient of 3 in my balanced equation, so I have a total of 6 of those bonds. The hydrogen oxygen, within the water, I have 2 moles, and then I have a coefficient of 4, so a total of 8 moles of those bonds. Let me just grab those values off the table. All of the values here, the endothermic, are all positive. The values here that are exothermic on the formation side, I'm going to make all of those negative. When I take the difference between those, I find that it ends up being an exothermic reaction. Now, I said earlier about how if you can make a sheet that would summarize all the information, it's a really good study skill. It's a really good way to consolidate and bring together your information. As we've gone through the video, this is the information that I told myself. Something about potential energy, about Hess's law, how I make sense of the different signs. I have a specific heat one, my plan for calorimetry, how I want to connect the reaction to stoichiometry, and the delta H value. How would I write a standard enthalpy of formation? How would I use it? And how do I think about for the bond enthalpy? These are my reminders. They might not be your reminders, but it's really important, I think, to take a whole chapter. See if you can make 1 page of your reminders, your strategies. How will you identify a problem and what do you want to remind yourself when you solve it? I think it will really give you a lot of confidence as you work your way from one chapter to the next.